it is immediately obvious from the definition that this equivalence relation is actual equivalence relation. Of course, it is reflexive, it is symmetric, and it is transitive. Why it is transitive? If we could go from W1 to W2 and from W2 to W3, then this sequence of terms will already give us equivalence of W1 and W3, because the sequences between have to satisfy a milder condition. Yes, and so it is, the problem is here it is W2, but W2 is actually better than it required, so we have already a chain that satisfies this condition. So, in other words, we have indeed we have an equivalence relation. Now, and then the equivalence classes of this equivalence relation will be the elements of the group which we are going to construct. But then we also will have for them a representation inside one layer maps, which will be important here. So it just means that we may have such kind of structure, cell after cell after cell. It may be several times. It may touch. Now, subject to the condition that on each side these words are semi-canonical with a constant number 1. Because if some side of this would be semi-canonical with not number 1, with some condition less than this, then no path going through this side would itself would in fact be semi-canonical with constant lambda 1. So we can delete all these sides, so we always can assume that on both sides this condition is satisfied. But the actual passing it may be something that does switch sides, but it itself should be also subject to the same condition that it is semi-canonical with constant lambda 1. Okay. So this is our definition of the elements of the group. The next task is to define their product. And the product, of course, should be stable under this equivalence relation. What we will do, we actually use this one layer diagrams for defining the product. By the way, it is easy to see that we have here between these one layer diagrams, we have an inclusion relation when maybe some of them may have less region. So if I take only this, assuming that this constant is satisfied, that this will just it will be one layer which is included in this one. So then it is also easy to see that there, under this inclusion relation, there is a maximal one layer method. Contains all the possible such cells. Of course, none doesn't violate this, because maybe some of that, if we take and compare it with the other, so the union will be already of the same type. Because if we take the union, what we mean the union? Assume that we have, this was one layer type, and then we on the side of it we may have some maybe completely different. One layer map. But then it turns out that these two situations, either we have the cell on one side and not have another side and we add it, or it could be that when we have cells here, they must coincide because they are defined by the R, is decided by the R chart of the world. And then, of course, this cell will be identified as this one. Therefore, we can take a union of all of them, and this will be maximal one layer map. This corresponds to a given element of this group. But this is clear. It's easy. This is an easy combinatorial argument because when we compare the cells, if they are one in this way, then we just can combine them. If then they can identify flipping this. In any case, we have the maximal chart. We have the maximal one layer. Okay.
The maximal one is singular? Is it singular, the maximal?
But in which sense singular? Unique?
Unique.
Yes. Because we take the union of all of them. And the unions of all of them will be of the same type. My point is that we take two of them. We can just take their union, it will be of the same type. Then we take the unions of all of them. So this will be the unique maximal one layer map for a given element. Okay?
Given element
of the group we're going to construct for the given equivalence class defined in this way. Now we would like to define a multiplication of this. So, just in
but
yes.
we started from generator and relations.
Yes.
And now we're going to construct a new group. Yeah?
Yes, I'm going to construct a new group and then to prove that after all these isomorphic resolutions. Now, we have two such words. They correspond to certain one-layer maps. And then we have another one-layer map. Now, instead of multiplying them, let me compare the first with the inverse of the second. And you see, let me compare the second with the inverse of the first. So we are looking, so we have here the second one, and when we just, what's the inverse, we just take it in the opposite direction. So we have, this is the second one, whatever it means. And then we have the first. Now, if it starts with a word, and then in some place there will be a non-equal letter. May happen, we compare them. This is a word, we compare them. If in some place this letter will be different from this is A, this is B, until we have the same word U. So what happened? The first one ended with the word B minus 1, U minus 1. This one started with UA, So this will cancel out, and then perhaps letter B minus 1 A, these letters will not cancel. So, this is the first possibility that we encounter a difference already in the beginning of it. Then, what will happen? We just so we have this one. And whatever we have here, we just take this and reverse this to this B and take this one. And then this will also be a one-layer map. Now, of course, one has to ask whether we might have some more region here, and we will examine this later. It may happen. But assume that the original was the same. Then, when we have here this cell, so it might be the possibilities. Maybe there is no cell here, or there is a cell here. If it is a cell, it must be the same cell. Because this part is, in any case, it should be bigger than 1 minus lambda 1 minus 2 epsilon. And this is enough, this is much bigger than epsilon. So if we have a big enough common part, it should be just the same part. And then we inspect the next one, etc., etc. Until either it could be the same product, is that they just cancel out. Or in some place we find a difference. So the difference could be just where we have cells or when we have letters. So we have two different reasons why there is a discrepancy between these two maps. Now, if here, what might happen for the cells? So the last time we had an identical cell, this was the last identical cell. Then the next one might be different cells. How could it be? Because we have one cell here and one cell here also. This could be no bigger than epsilon, and they may overlap in any way. Not just it should be disjoint, it could be just this part also, doesn't matter. It could in any way, but in all ways the common part is less than epsilon. So then what will actually happen is that we are going from this one, coming here, and then it depends on the disposition on this cell. For example, maybe that both of them are in quite different positions on this cell. And then we have a possibility to either we will go this way, or this way, or both. It depends on the lengths. If both lengths are less than lambda 1, we will choose both of them. If one of them is bigger than lambda 1, we choose that one. It is impossible that all of them are bigger than lambda 1, because 2 times 2/3 we cannot meet. So one of them may be. So in any case, we may include or not include this cell depending on the numbers which we meet here. For example, here this was very big, so we will not include this, only this. It could be that we might include both of them or just one, depending on the length. In any case, now, and then we obtain a new a new one-layer map, which goes in the way as it was here, and in the way here. And this one-layer map will be a product of this, in this sense that all the passes that go through this with the condition lambda 1 will be the equivalence class of their product. So this is a geometric way, say half combinatorial, half geometric way to define the product. Now, because the one-layer map was an invariant of the equivalence class, because we just take the union of all such maps that corresponded to all the words in the equivalence class, and this union was defined with the same properties, so it is uniquely defined by the element. Therefore, this construction immediately says that the result is depends on the equivalence classes and not on the choice of the elements inside this equivalence class. So, and what we have exactly, and then what we obtain is in fact a kind of a sim triangle. Sim triangle, so we have three sides. We have one side corresponding to the second word, one side corresponding to the first word, this was it inverted itself, and we have one side that corresponds to their product. Actually, because this was the first word type, this will be this. Will be the one-layer map corresponding to this will be the one-layer map corresponding to the product of these two words. Now, but this was an easy case because we had some ranges in the between, so it might belong or might not belong. In the case it belongs, so the structure of this map is some middle region. We have a middle cell in the middle, which actually touches on all the three words. But maybe the discrepancy was in the letter. So this corresponds to the situation. So we do not have here a region in the middle. So it means that each of these regions may touch on two of these words, but not on the three of these words. Any region touch either of the first or the second or the third, the first or the third, and here we have a region that touches all three of them, or they may have no region in the middle. So we're actually left with two alternatives for this product of, actually it's the product of one-layer maps, and then the elements, the words that actually present the group elements live inside these maps. So for the first word, any word living here will be, if it satisfies the SC condition with lambda 1, it is representative of element of the first one. If it lives here for the second, and if it lives here for the third. So this is the way how we can see this situation. So for example, here it might be such a way. It might be this region. Now something here and something, even something in this way. Even could be that we have a point of valence 3 here, but nevertheless we do not have an edge that is on the side of the wall. But here we do have a cell that borders with three of these words. These are two possibilities of the thin triangle, and then the first factor, the second factor, the product live inside this side of this thin triangle. Okay? Okay. Because the common part of two cells is small, therefore this is easy combinatorial situation. Otherwise it could be difficult, but here it is easy because the common part of cells is very small. Okay, now, so we have now a certain product, and we have to show that this product is actually associative. So let me first recall the situation in the free group. Why the product in the free group is associative. So if we do the third condition, so we have for the two product triplet. This is a product in the free group is defined by a triplet. We have the first word, the second word. This is the cancellation. If it was indeed, it could be of length 0 or bigger. So the triplet, this is a record, this is a particular case of the trio cancellations, which is just a triplet. Now, if we take 4 elements, so actually it means that we have to compose 2 triples. So there is, because we can take the first and the second.
4 elements of the generator?
To that?
4 elements of the generators?
For the free group element. In the free group. In the free group, do not have themselves, just we have only cancellation. And then the product of the word is represented by the triplet. And then we have the first word, the second word, the product of them. Now we have to take the product with, so this is the product, we have to take the third word. Now then here basically it is 3 situations. 1, 2, maybe here. So this was the third word, and here, and this is the product. Or it may be 1, 2, it may be precisely here, the tetrapod, or it might be, it is this, so 1, 2, 3, and this. So actually we have 3 configurations. 3 configurations, which means, so think of this way. This one is known, this could be so this is 1, this is 2, this is 3, and this is a product. 1, 2, 3, and this is a common part with 1 is also cancelled. So here the first and the third cancel out. Here they do not. So this is the first, the second, the third, and the product. So what happens here? Only the first cancel out with the second cancel out with the first, but not deeply, and the product will be this way. Or here it could be precisely the first to the second, the third, and this is the product. So this is a situation in a free group. So basically we have just 3 configurations. Now, here when we return to this group, so we have here actually a composition of 2 thin triangles. But we must take into effect that we have the triangles of 2 sorts with a region in the middle and without a region in the middle. But given this, we can now just have all the kinds of the configurations, which will be a little more complicated, but basically it will be the same. We compose two. How do we compose two thin triangles? The question: how do we compose two thin triangles? Just one moment before it. Just I said why. Given this, how do we know that the product in the free group is associative? Then, for the situation, just what happens here? We can first cancel out this, then cancel out this. Or vice versa. We can first cancel out this, then cancel out this. Now it is clear that we perform in this order or the other order, the result will be the same. Because we know if we cancel one letter here and one letter here, in this order, in the reverse order, the common result will be the same. So we can perform these cancellations in any order, which one by one, so the result will be this one. This already proves the associativity in this particular case. Now, what happens here is just the same. The interesting case is here. That what happens? We first can cancel out this part. Actually, we have to cancel everything here, but we don't do it. No, excuse me. Whether I know the, is it correct when I do? Yes. This is the first, the second. So what we can do, we can cancel out this. So what was the cancellation originally? This cancelled, then this and this cancelled. Otherwise, we have to cancel this and then this and this. But we may perform in other way to cancel out this or this, it doesn't matter. We have the same result, and then we do the cancellation of this one. This proves that the cancellation is the product of the free group is associative. Well, we have known this fact in advance, but we have now a combinatorial overview of it. And the same argument will work in the case of composition of thin triangles. Let me explain it more detail. So, let us first assume that we actually have four cases, that both of them have a region in the middle, one but not the other was the one, and none of them have a region in the middle. So assume first that each of them has a region in the middle. So, in the first case, so the first triangle was this one. Let me show it. The second triangle was this one. It may or may include or not include the middle region depending on the length. Now, in any case, so this is the first, the second, the third, and the product. This is the first, the second, the third, and the product. So, if we perform in the first order, so we actually cancel out this part. So we're left with or without this region depending on the length. If it's too big, we throw it out. If it is not big enough, we take it. Now then we have then cancel out this. So we have now this triangle. No triangle actually is the same. And then we cancel it with this triangle. And then this left out and we have the situation. But we can do in the other way. We can start with this part and cancel it. And then we cancel out this one. The result will be the same. Because it means that we just delete certain cells, but in different order. And the result will be just circumventing all the remaining cells. Now, and actually, it could also be that these two middle ranges could be close to one another. It doesn't matter. This does not change our situation. Now, it could be that it's the same. And then we have this one, this one, this one, and this one. So this is the first word, the second word, and the third word. With the first and the second, we cancel out this part and leave or not leave this region and cancel out this. Or vice versa, first this and second this. Then, in any case, we left with this word. And it depends whether or not we include this cell, depending on what is the length of this part of it. In any case, this is the same result. Now we have the other situation when it is of this type. Of this type, also we have now, we assume that we have a middle region here. So this is the first word, this is the second word, this is the third word, and this is the fourth. Now, either we take the first and the first, then we have to cancel this one, then the product should cancel out this one and this one. But we can do it otherwise. We can cancel out this part, stopping here. Cancel out then this, and then perform the cancellation until we need this part. Or vice versa. We first cancel out this one, then this one will meet exactly the same situation because we delete just the cells from this type in different order, and then we perform the cancellation here. So whatever we end up with the same, it will be the same one-layer map. And what are the elements of this group just passes in this one-layer map that satisfies this lambda 1 condition. So this proves that our case when we have an edge and the letter in the middle. When we do not have a cell in the middle, it is the same but simpler. Because we just ignore the zero, but our argument remains the same. It defines, it splits in three cases. When these, according to the same situation in the free group, when these cancellations are far apart, then it doesn't matter to change the order, or they are roughly with one center, so this one or this one also the same, and the different situation that here we actually have a cancellation between the first and the third. But to reach it, either we cancel out this part and then this part under the end, or we cancel this one and this one under the end. We can do the middle situation. We cancel this and this, or vice versa, and then we have come to the same intermediate result, and then we continue the cancellation until we reach the result. In any case, it says us that this operation is associative, just for this simple combinatorial process. So now actually we have constructed first a semigroup. Now needs a prime inverse. Inverse immediate. Because what is the inverse of the one layer map? Just this is a map. Just take it, flip it in the other position. So this will be the inverse of it. And of course we cancel out to a unit element. So this is a group. Now let us call this group G1. The original group was G. We have G1 is a group of equivalence classes with this cancellation, with the product. The group of equivalence classes of semi-canonical rounded numbers.
So to define G1, we need to have a measure for each element of R.
Yes, and be sure that the measure of common part is small. Otherwise, this doesn't work because we need a chart. We have to know that there are only small overlaps of the elements of the chart. There's nobody inside the other. Nobody is covered by these two values. Just given this combinatorial condition, we are able to perform this construction. And of course, I didn't check to a best constant, but one who wishes can just like what is the best constant that still allows this construction. But will not be inside the scope of this course.
And the constant doesn't depend on the measures we define on R?
No, we just assume that we take a small epsilon, we assume that these measures are chosen in such a way that the common part is able to take a small measure. Okay, now the question is whether this new group is isomorphic to the original. So we will try to have two homomorphisms. One from G to G1 and other we have other direction and check that their product is identical on each group. If we are able to do it, then it means that the groups are isomorphic. Okay, so in one direction, what do we do? So because this group is given by generators of relations, we have to define it as the generators and then to check that the relations are satisfied. So lambda of x will be the equivalence class of x. X is one letter, and obviously it is short enough, so then we have to check that if we take the product, so if we take R as a relator, R in R, we have to check that lambda of R is equal to 1 in this group of G1. This is what we have to check. In order to define it, because the group G is given by general relators, we have to check. We define it on the generators. We have to check that it sends all the relations to 1. Let's check it. So we have the word R. The word R, after all, is composed of letters. And then we try to multiply. Everything is well until we reach lambda 1 of this. Then equal to its complement. This is in a sense a one-layer map with one cell. And then when we add all the rest, we cancel to one. So we have the result of it, this is one. So we actually have defined this one. So now we have to define mu in the opposite direction. Mu from G1 to G. Okay, this is immediate. Because if it ever goes, so which is a corresponding curve in G. But because the different representatives of the same class are inside this map, and these are relations in R, so we have this well defined. Because different equivalent words give us the same result. So we have this homomorphism, and the product corresponds to the product as well. So now, why we have what will happen with lambda mu? I mean G1 to G to G1, and what happens to mu lambda G to G1 to G. So we take here a letter, it goes to the class of the letter. The class of the letter is the same letter, no problem. Here we have a vowel at equivalence class of this. It goes to this letter, it goes to this letter. So on both sides we have identity, so we have proven that this group size is. So today is good. So what happens is we have a constructive definition of this. Instead of speaking generally with generous relators, and then we don't know what happened, here, because of the spoken relation, we're able to construct it specifically.